Well, good morning. We are recording, and let's go from current slide, which now we are there too. Okay, we finished examples 1 and 2 in section 2.5, implicit differentiation, and we're starting here. Before we get started, any questions on anything we've done so far? And as DeMarcus has already pointed out this morning, with many tears and woe, sort of good news, bad news situation coming up. The good news is next Wednesday, not this Wednesday, but next Wednesday, is the 4th of July, and that is a state holiday. The bad news is that means we won't be meeting next Wednesday. This Wednesday, yes, but not next Wednesday. So if you come, just get started without me. I won't be here. Okay. So, any other announcements or any other things? Any questions? All right. Let's get going on implicit differentiation. It's meaningless to solve for y dx in an equation that has no solution points. For instance, this one, x squared plus y squared is equal to -4. Don't even try. I mean, you can go through the motions, but this has no points. You can't add, dealing with real numbers here, and that's where we are. If you have any real number here and square it, the least it can be is 0. It will be greater than 0 most of the time. You take any other real number here, y, and square it, the least it can be is 0. Okay? It can't be anything less than that. It could be positive. And you add two non-negative numbers together, you surely can't get a negative number. No solutions. Okay? So don't try differentiation, implicit differentiation, when there is no solution. If, however, a segment of the graph can be represented with a differentiable function, then dy dx will have meaning as a slope at each point on that segment. Now recall that a function is not differentiable at, number 1, points with vertical tangents, okay? Number 2, points at which the function is not continuous, okay? Points of discontinuity, okay? Now, also remember this. Just because the function is continuous doesn't mean it's necessarily differentiable, so that still won't work either, okay? So let's see, with that as a lead-in, sort of a segue, you might say, then you would think the next example might be illustrative of that. This is Will, I know, but I got to find you, right? Okay. Got it. Okay. Just getting ready to start example 3. Let's see if no, they don't do example 3. Shame on them. Okay. Well, that looks like a good place to do example 3. Well, let me get my pen set up. All right. Example 3. If possible, another caveat here, represent y as a differentiable function of x. Here is the a. X squared plus y squared is equal to 0. Okay? It says represent y as a differentiable function of x. Okay? What you think? Any ideas?
0 plus 0. Equals 0.
Say again?
Only two values that can go for x and y would be 0. Because
you got it. There's only one point for which that is even defined, and that's the point 0, 0. So it's sort of hard to give that as a y as a function of x. The closest you could come would be this. Y is equal to x as long as x is equal to 0. I mean, that's about it. And I wouldn't even bother to waste my time writing it. And it says it does not define y as a differentiable function of x, so don't even mess with it. Okay, here's the b part. X squared plus y squared is equal to 1. Okay? Can you express that as a differentiable function of x?
yes. Yes.
Yes. How so?
1/2 plus 1/2.
Second?
Yeah.
You may have said it right. I just couldn't hear.
I don't think I said it right. I said 1/2 plus 1/2. That's the only
Well,
one.
no, there's lots of other values. In fact, there's an infinite number of values. They're just limited to a very small domain, but there is an infinite number of values, which makes that a solution. And Daniel's here. Okay? Except for poor old Nolan down there near the end of the alphabet. He's the only one. The top half of the alphabet is doing great. You're holding up the whole bottom half. Okay. Way to go. Okay. So, there's an infinite number of solutions. Anyone want to hazard a guess where they live? 1/2 is certainly in there. What would be the x values for which this would be defined? Okay. It might be easier to go in and simplify. What they're asking for, maybe simplify is not the right word. If possible, represent y as a differentiable function of x. Okay? Now, what's that saying is, in other words, solve for y. Okay? Represent y as a differentiable function of x. What would be your first step to solve for y?
X over.
Okay, what do you mean by that?
Minus x.
Yeah, subtract x squared from both sides of the equation. If my pen would write, which it's having trouble doing. Okay, and this would yield y squared is equal to 1 minus x squared. Now I want to solve for y, not for y squared. So what do we do next? Anybody? Not yet. Yeah, take a square root. Y is equal to, and you tell me what that is. All right. Awfully close, but not quite any cigars. Why not? What are you missing? Anytime you take the square root of both sides of an equation, you got to put it plus or minus. Okay? Because not only is square root of 1 minus x squared y is equal to that, y is equal to negative the square root of 1 minus x squared. This forms a circle, radius 1. That's not a function. The function that's top half, that's a function, that's with the plus there. The bottom half, that's a function, that's with the minus there. So these are two functions of y that are differentiable functions of x. Where are they differentiable functions of x? Not everywhere. Any ideas? Can you give me a value that won't work? 1 will just barely work for a function, but you're right, it won't be a differentiable function at 1. Why not? Say again?
But anything that's greater than 1.
Greater than 1 will certainly be out of the question. Okay? 2 would fail miserably, right?
So it's negative infinity.
Say again?
Like the domain's negative infinity.
Okay. So give me something in that domain that you guarantee me will work. Negative 2. Do it.
1 minus.
Oh! What's wrong with that? It's also outside. So what is your domain? Negative 1 to 1. Okay? And you tell me what kind of symbols to put around that. So negative 1 is less than or... Ooh, I just blew it. Okay? I was going to do it in interval notation. That's why I said symbols, but then I started writing like this, so let me do this. Okay? That's one way to express it. Have a left off anything. Should we have equal signs there? Okay, or bracket. Okay, that's If you've written it in interval notation, been -1, 1, and you say put brackets there. And I'll agree with you halfway. The function is defined there, but it's not differentiable there. Why not? Okay? Would doing a quick draw of the function work? You want me to do the top half or the bottom half? Okay. Here's the top half, something like that. That's not very pretty. I'll do the bottom half in a different color. Y'all give me a color. Second? Pink? Is that what you said? I don't have really a pink. I have this bright red. Will that work? Orange. Okay, let's go back to orange. Okay, he's real picky today. Okay. All right. So there's the bottom half, sort of. Okay. Now, is this differentiable at -1 and 1? Why not?
I don't know, because it's a circle.
Second?
I don't know, because it's a circle. I thought like
It is a circle,
it's
yeah.
a vertical line test.
Ah! Okay, now, okay. Vertical line test defines it as function. That's why I couldn't include both of those. Okay? Well, either one is a function. Okay? But, what is that differentiable at ±1? Why not?
Horizontal line test.
Okay. All right. Here's the derivative there, 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 there. What's the derivative at the ±1? What's the tangent line? Say again?
I'm not sure.
Okay.
Yeah.
All right. Anyone want to make a guess? What's the tangent line at -1 or +1? Just describe it to me, huh? The tangent line is 1. Okay.
Is it all constant?
Say again?
Zero.
Say again?
Is it constant because it's 0?
No, it's the tangent line.
Oh.
Okay. The tangent line is that there. Is that here. This here. What is it at the endpoints?
It's bigger than 1 and 1.
That's the place where it
It's
is.
vertical,
What
that's
is
what you're trying to get at.
It's a vertical tangent line. Not defined. Okay?
That's why you got excited when I said vertical line test.
Yeah, well, okay, the vertical line test is the thing about whether it's a function or not.
I see why you got excited.
Yeah, I know, yeah, I get excited easily. No, that was close, but no cigars, okay. Let's go forward one slide. We have to get a while to get there, but, okay. Recall that a function is not differentiable at A. Points with vertical tangents. That's why it's not differentiable at -1 and +1. Everything in between, yes, but not at plus or -1. Okay? So, therefore, we can't put brackets. We have to leave parentheses. Okay? Two things I got to do. Erase and get my color back. So it was actually correct when I left off the equals here. The function is defined at plus or -1, but it's not differentiable at plus or -1 because at plus or -1 you have vertical tangent lines. It's not differentiable. Make sense? Okay. All right. So close. Okay. Number C. Okay. Can we do it here? Let's try it. There it is. I couldn't find it. C is x plus y squared is equal to 1. Okay? Now the question is, represent y as a differentiable function of x if you can. The question is, can you? Yeah, okay, do it for me. First step.
Move the x.
How do you do that?
Move minus x.
Subtract x from both sides of the equation. That's good. And that gives you
Y squared equals 1 minus x.
y squared is equal to 1 minus x, right? Okay? Now, I want y, not y squared.
So
Square root. So y is equal to,
square root of 1 minus
second. All right, plus or minus the square root of 1 minus x. Okay? Now, that means there's actually two functions for which this is defined. Now we have to figure out where, if anywhere, it's differential. What's your guess?
The domain is negative infinity.
Okay?
Negative 1. And unison.
Okay, so you define the domain of the function as negative infinity to negative 1. Is that negative 1 or?
Well, then we're going to do the little weird u, and then you do that 1.
Okay. Oh, you want weird u's, huh? Okay, I got a weird u. And what else?
1 to infinity.
Okay. All right, and you want some sort of symbols. I know infinities have parentheses. What about the minus ones and ones?
Brackets.
Bracket on both of them?
I think so.
Okay, we'll see. All right, now, let's see if this is making sense. I agree wholeheartedly that at negative 1, this certainly works.
Oh, wait, I messed up.
Uh-oh. Wait. Thought it was a special day. Never mind.
It can work at 0.
The code, right?
Yes. Okay.
Take this second. Anyone else come in? That's what.
It can work at 0 too.
It can work at 0 also, okay? Okay, which one of these do you want me to write as a 0?
You probably know what's best.
What's that?
You probably know what to do with
Well, you told me it would work.
Well, I mean, like, the 0 can work, I forget how to put it in.
Okay. How about this? Can I do that?
Yeah.
Okay. All right. Now, 0 worked. We got that far. Anything else will work? Any from the negative infinity to 0, I know that's going to do okay.
Positive infinity.
Second,
Positive infinity.
positive infinity will work. No, it won't either.
It'll
Okay.
be negative.
Second, it'll make that negative, absolutely. So how far can we go toward positive infinity before we can't get it working?
You stop at 1.
Stop at 1. Good deal. Okay. Now what are we talking about now? Where the function's defined or where it's differentiable? You tell me.
Where's
Okay, defined includes the 1, doesn't it? Because you can put a 1 in there. 0, plus or minus 0, yes, that's no problem there. Is it differentiable at 1? No, why?
Is it 0? It'll be 0 at that point.
Okay. All right. You know what this one looks like? Let me erase the one above so I can use that same graph. Okay. What does the graph of that look like? You told me that 1, 0 was on it, right? Okay. How about when x equals 0, what do you get? Yeah, you can get positive 1, or if we're on the orange side, we get negative 1, okay? And then I'm going to go out on a limb and go out to negative 3. What happens at negative 3? X equal negative 3.
4.
Okay, square root of 4, which is or negative 2. So that was at negative 3. And that was down here at negative 2 or up here at positive 2. Oops, that's not what I wanted. That's what I wanted. Okay. Any idea now what this is going to shape out to be? No, absolute value function. I may have this plus and minus 2's too far up. Whoops. Yes. Whoa, I thought I got orange. Okay. Yes, a horizontal parabola. Okay? Either the top half or the bottom half. Okay? Now, go back to the question that I had. That's defined, either the plus side or minus side, the function is defined from negative infinity to 1. We established that. Is it differentiable from negative infinity to 1?
I don't think it is based on the rule we have. Again, it says at a point. I didn't get the rest of it.
Okay. Same as before. Differentiable means it has defined tangent lines, but what happens?
Oh,
Vertical tangent lines, so no, it's not defined at x equal 1. So it's defined, the function is defined at 1, but it's not differentiable at 1. So we have to take that off for differentiability. Well, I got to get my pen color back. Okay. It didn't come back. Okay. Yeah. Okay. Now, on both of those, there was another way to approach it. Okay? And I think this may have made it easier to see, but I was hoping with the graphs and stuff that would be visible and you see why it's true. But let's do it the other way. Let's actually take the derivative and see what we get. So on that first one there, how would you take that derivative? Now, either one of two ways. You could either take it of the y down here, or you could take it of the original function. Which is easier, you think? Original, okay? Take the derivative there. What do you get? 2x
plus 2y.
2y. Y prime equals 0. Now what are we solving for? Okay, how do you do that? Subtract 2x from both sides. Okay, and that gives us 2y, y prime is equal to negative 2x. What's the next thing you want to do? Okay, divide both sides by 2y. That would certainly work. Okay. Now, here, everything but y prime disappears. Here, the 2's go out. Okay. And what does that leave you with?
Y equals negative x.
Okay, y prime is equal to negative x over y. Okay. Now, what was y? Now we go back to this. Okay? Y is either plus or minus the square root of 1 minus x squared. So this would be negative x over plus or minus, and you probably should do them separately, the square root of 1 minus x squared. Okay. Now, when you do your derivative that way, don't you see more clearly why you have to exclude plus or minus 1? because that would make a, so either plus or minus 1 for x, what you wind up in your denominator.
Basically, zero.
Figure?
Zero.
0, exactly. 0 is all right here in defining the function. Yeah, no problem. But once it goes in that denominator, no, it's not all right anymore. You still can't do the negative numbers, so all those were excluded. But now this excludes x equals plus 1 or minus 1. Because the derivative is not defined for x equals 0. Same thing will work here. This will be a little bit different, but you'll wind up with this in your denominator. Well, yeah, you'll wind up with this in your denominator again, and you can't have x equal 1 in your domain. Not for the derivative. It is for the function, but not for the differentiable part of the function. Does that make sense?
Yes.
Okay. Now, they didn't do it that way, they just did it by the graph, but I thought maybe this would make it a little clearer to you why it can't be. Okay, they don't have example 4 either, so is everybody okay with this? I erase it? Okay, moving to example 4. By the way, we're on page 146. I didn't tell you that when you came in to cut over. Now, example 4 is also found at larsoncalculus.com, or at least an interactive version of this type of example. So maybe not the exact example, but something very close to it is there. And here's what it says. Find the slope of a graph implicitly, okay? Determine the slope of the tangent line to the graph of, so we're looking for the slope of the tangent line, that's a T for tangent line, of the graph of x squared plus 4y squared is equal to 4. Now this is just sort of a question you don't need to know the answer, just wondering if you do. Does anyone know what that plots as? X squared plus 4y squared equals 4. Okay, I would agree with that under 2 conditions. If either that 4 was a 1 or this 1 was a 4, then that would be a circle. But the way it's thought, it's not quite. What have you done to the circle? Stretched it and made an oval. Oval is one name for it. Anyone know the more mathematical name for it? Ellipse. Exactly. That would be the equation for an ellipse. Okay? You didn't need to know that to do the problem, but they drew one for you, and there it is. Okay? It says determine the slope of the tangent line to the graph of that function at the point, and the point given here is root 2, comma, negative 1 over root 2. Okay. Now, cynic that I am, I'm not going to proceed any further until I convince myself that this point is indeed on that curve. What if they gave me a problem that's at a point that was nowhere near the curve, and then I waste a lot of time and I can't figure out what the slope of the tangent line is because it's not even there. So how do you confirm that that point is on that curve? Second? Okay, good answer in most questions that I ask here, but in this case, not. Plug it in, play, okay? So the x value here is? Square root of 2. And if you square that, you get 2, okay? The y value is? Negative 1 over root 2. And if you square that, you get 1 over 2. 4 times 1/2 is 2. And this was? Plus equal. Didn't know you'd be doing such high-level math today, did you? Okay, 2 plus 2 is 4. Got it. Okay. So, yes, that point is on the line. I can proceed. Okay? Now, is your chance to answer the question, what's our next step? Hit it, Nolan. Take a derivative. How do you take a derivative in one like this? Anybody?
Same way we did it last time.
Second?
Same way we did it last time.
And how was that?
2x
Okay, implicitly, okay? 2x plus 8y, y prime equals 0. Okay? Why are we doing this? Because I told you to hit it, didn't I? Okay? Why are we taking a derivative of this?
So we can get the slope.
So we can get the slope. Perfect, okay? So where do we go from there?
X over 2x.
Okay, how do you do that?
Minus 2x.
So, okay, subtract 2x from both sides. Okay, and that gives us? What does that give us? 8.
8y. Y prime equals 8 2x.
Okay, and then what? Divide by 8y. Okay, that will wipe out here. What goes out on the right-hand side? Anything? Second? Oh yeah, that turns into what? 1 over 4. Got it. Okay. So there we have y prime, which, by the way, represents the slope of the tangent line at, and this is going to be anywhere, it's going to be minus 2x over 4y. And it's pretty obvious from that y can't be. Second? Okay.
You say it again?
What? From this expression that the slope is minus 2x, I write 2 up there, minus x, duh. Y'all let me get away with it too. What were you doing? Okay. Minus x over 4y. My question was, what's a pretty obvious value y cannot be? 0, exactly. Okay. Now where is y equals 0, by the way? Where is y equals 0? Any graph of anything. There's a graph board over there. Where's y is equals 0? Second? In the middle, or certainly the origin. Second? Someone said something else. No, I said where y is equals 0. Second?
It could be 0 across that whole x.
Ah, that's it, on the x-axis. Y is always 0 on the x-axis, including in the middle, right? So y is 0 on the x-axis. So the figure you have in your book, y can't be 0 at those ends of the oval, right? And why is that?
Tangent lines.
Vertical tangent lines, exactly. So that's why y can't be 0, okay? Just getting back to that. Reinforcing the point. But what we're interested in is what the slope is at that point there. So guess what we do? At that point there, we're interested in what is the slope. Plug it in, plug it in. So m at root 2 negative 1 over root 2 is negative. Get out of there. Okay? What's your x? Okay, no, it's root 2 over, and then your y is, wait, it's 4 times y. 4 times, and what's your y? Negative 1 over square root of root 2, right? Well, one thing I can see I can do right now, the 2 negatives make a positive, so I don't have to haul those around anymore. Okay? Now, I'm going to rewrite this as root 2 over 4 over root 2. Is that okay? In most states? Okay? How do I process that? How do I deal with it?
So you move
Absolutely. This is the same as root 2 divided by 4 over root 2, right? Which is the same as root 2 times root 2 over 4, which indeed does exactly what he said. Root 2 times root 2 is? Second? I couldn't hear. 2, exactly. Over 4 is? 1/2. There's the slope at that point. Okay? Now let's see if that makes sense. Okay? Your x value is root 2, which is somewhere out here. I don't have the graph here. I'll do it in just a second. And then you're at minus 1 over root 2, which is somewhere down here. It is on the ellipse. And sure enough, that has a positive slope, not a very great positive slope, 1/2. That's exactly what it looks like. And since they don't have the graph here, let me just do in a quick rendition of the graph. And let me just give you a hint or two on how you do these. The standard form for this ellipse, by the way, is x squared over a squared plus y squared over b squared is equal to 1. That's the standard form for an ellipse. You're not supposed to know that yet. I'm just letting you know. Well, how would we get that to be a 1 over there? You divide both sides by 4. Right? Everything on both sides by 4. This is such a pain in the neck. So this gives you x squared over 4 plus y squared over 1, 4 over 4 is 1, is equal to 1. Okay. Now, what would your a squared be then? This is the standard form. This is the form we've got. A squared is obviously equal to 4, so a is equal to?
Would it be 2 since it's a squared?
Okay. A would be 2, a squared is 4. Yeah. So plus 2 or minus 2. Okay? And what would your b be?
1.
Okay? Plus 1 or minus 1. There's your ellipse. Something that looks like an oval. Okay? Pretty ugly, but you get the general idea. Okay? Now, where in the world is root 2? Approximately. What is root 2? Punch it in your calculator. See what you get. 1.414, right? All right, good. So you're either up here or you're down here. Well, this told you you're down here at negative 1 over root 2, which, by the way, is about 0.707. So that looks about right. And what's your slope at that point? Sure enough, the tangent line looks like it's about 1/2. It's a gentle slope, not very great slope, but positive. So yeah, that looks pretty good. Right? Now my drawing is pretty ugly, so probably off a little bit there. The one in the book, probably a little bit better, but not much. Okay.
Where's the 1 divided by root 2?
Okay. It's down here, and it's negative, and that's 0.707, negative 0.707. Punch that in your calculator. So negative 1 over root 2.
Yeah, good.
Okay, so it's down here, Rob, so that gave you that value, this value. Something about that. Okay. All right. I drew the graph and then picked out my point, but never mind, that's beside the point. Okay, any questions on that? Then let's move to example 5. And they do have example 5, so we'll move on to it. Here we go. Determine the slope of the graph of this thing, okay, at the point 3, 1. I think I've already indicated to you what I would do first. before I'm going to waste a lot of time on this problem, I'm going to make sure. Yeah, I'm going to make sure 3,1 is indeed on that curve. That's an ugly looking function in my mind. So let's see. If I plug in a 3 for x, what does that become? Okay, and a 1 for y. 1. 9 plus 1 is 10 times 2 is, squared is 100. That's 100, so that's okay. And then this would be 3, which should be, if that's indeed true, x times y. Yes. Okay? That looks like it's on the graph. I didn't go out and bore you to tell. Plug it in, figure it out, you'll see that's indeed true. 300 equals 300. Okay? So, I feel better about that. How do I determine the slope of the graph at that point, since I know that point's on the graph? Take a derivative. Good answer. Okay, and how in the world do you do that here? Second? Chain rule, you're absolutely right. How does that work? Anybody? How does that work here?
It's going to be 6.
6, okay. The outermost function, take derivative of the outermost function, which is your squaring function. So it's 2 times the coefficient 3. That would be 6 times
X squared.
X squared. Say again.
X squared
Plus Y squared to the first power
times
times
2x
2x
times 2y.
What do you say after 2x? Times? I don't think so. Plus. Oh, you did. I thought that's why I asked. And I thought you said times. Sorry, my hearing's not good. 2y y prime. Got it. Anything else? Huh?
Is it supposed to be squared?
No. You're done with the left-hand side, but you got a right-hand side.
Okay.
Second?
This be 100 y prime.
Okay, wait, okay. How about equal, right?
Yeah.
Okay. I didn't hear, but maybe I missed hearing you say it. Okay. Next.
100 y prime.
Okay. Now, what did you just do? Explain that to me, because I'm a little slow.
If you do the derivative of x, when the x go away,
Okay.
that's
So,
just 1.
okay, so what, you've made up a new rule for me that I'm not sure I'm familiar with this one. What rule are you using? Those two things are x, y. What does that mean when they're x, y?
They're together.
They're what? They're together. Yeah, they are a couple. Yeah, no, that's not what it means. It means, huh? Yes, you do. If there was a plus there, that would mean added. What does it mean to write two variables next to each other? Multiplied. So shouldn't we probably use the product rule? Let's try that one. And what would that be?
That'll be 100x
100x. That's the first one.
times 100 y prime.
Wait. How many times are you going to use 100? It's just a coefficient. 100x times.
Well, yeah, but like you keep the 100 because you did the power of it.
Okay. All right. You tell me the two things you're multiplying here.
I thought you were doing, is it 100x and then just y?
You can do it that way. It's perfectly fine. 100 is just a number.
100y.
Huh?
Then it would just be y prime.
Then y prime. Okay, I'll buy that.
And then plus,
Plus
it's going to be 100
100. He likes 100, I can tell.
plus then that times y.
I don't think so. Well, yeah, it is. Yeah, 100 times y. You're absolutely right. Okay. And that is a plus in between those two. I'm sorry I ran out of room. I was trying to write it all over there. So let's spread that out a little bit and see what we got. Okay, there's a factor of 6 here, and there's a factor of 2 there. So let's pull all that out and make it a 12. But there's a factor of 100 down there, so let's at least divide by 4. Is that okay? All right. Should I do that in more? Let's do it more. Okay, that's going to be a 12 x squared plus y squared times x plus 2y prime. Have I written the left-hand side correctly?
So why does the 2 stay in front of the y but not the x?
What did I do? What? Oh, no, you're right. You're right. Because I'm stupid. Okay. Now, that answer your question. Okay. Okay. And the right-hand side? Let's pull out the 100. That's common to both. And what do you have left? X, y prime plus y. Okay. Do you agree we've...
Can you explain how you got that 12 one more time? Like, what do you do?
Okay. Obviously, 6 is in front of this whole expression. These are 3 factors all multiplied together. 6 is out there. This is, can't do much else with that. This I can factor out of 2. Well, let's take it all the way out there with the 6.
Okay, thanks.
And that's why I took it out of both of them, even though I forgot to take it out of one. So, yeah. So that's where that came from. So, I know right now I can divide out 4, leaving us a 3 there and a 25 there. I don't know if that's any better, but at least the numbers are smaller. Okay. Now, what would you recommend I do next? We're looking for a slope. What does that mean we need to know? Okay. You know what? You actually could do that. So why don't we? You can plug it in anytime you want to. I guess we can go on and do it now. Okay? So what does that give us? 3 times 10. Is that what you said? Okay. Times okay, it was your idea to do it, so, huh? 3 y prime equal 25 times. Say again? We certainly could have. But you can do it this way too. I mean, there's nothing wrong with it. In fact, it has more numbers than you can do. More. So I kind of like this a little bit better. I wouldn't have thought of doing it, but I hate to say it, but it's a pretty good idea. No, I'm sorry. Okay. I don't mind saying it. What do you have next? 3y prime. I'm waiting. Plus 1. All right. Okay. Now let's see what we get here. 3 times 10 is 30 times 3 plus y prime is equal to 25 times 3y prime plus 1. Okay, because I don't like big numbers, I'm going to stop a moment here, divide both of those by 5, and make this 6 and a 5. Okay, a little more manageable. Now, distribute and see what we get. And you don't have to do it the way I do it. You can do it any way you want to. But I'm just showing you what I would like to do. Okay? What would that give you? Distribute. What you get? Second? 6 times 3. 18, okay. Need those calculators. Where are they when you need them? Okay, plus? Say again? 6y prime. You're distributing the 6 inside, right?
I said 6y.
Oh, you did. Okay, I'm sorry. Speak up. I can't hear. Okay. 6y prime is equal to 15y prime plus 5. I'm liking. We're cooking with gas now. Okay. Now what?
I would say simplify that down. No, wait.
You can't maybe move 5 over.
Take out 5.
Okay, yeah, we'll get right back where we were before if we start factoring.
Go ahead and move that 18 over.
Ah, yeah, okay. Which way you want to move it?
Move it the other way.
Say again?
Actually, no. Add that 5 to the 18.
Do what now?
Add that 5 to the 18.
Okay, I guess I misunderstood.
Okay.
Subtract the 5 from 18, don't we?
Yeah.
Okay. And what else might we do?
Move that 6y to the
How do you do that?
minus 6.
Minus 6y prime, minus 6y prime. Okay, and what does this give us? 13 is equal to 11. No, I don't think so. 9y prime. Okay, and guess what our 9y prime is then? Boo hiss. What is it? Say again? 13 over 9. Boy, that looks bizarre. It makes me wonder if we did something wrong. Oh, look at that. They got it too. Okay. Sure enough, there is your slope at that point. I never would have guessed that would be what it was. Okay? Now, if you'll notice what they did, and it's what I think Nolan was starting to wish he had done, but I said, no, that's not too bad. They kept it literal. They didn't plug in until they solved for y prime up here, and then they had x's and y's all over the place. Frankly, by plugging in early, we got rid of some of that. So I think it made the calculations a little bit easier, certainly easier to see. Okay? Just don't do it too soon, but this was a perfectly good time to do it. Okay? So in the text, they actually carried on through and kept it literal until they got y prime and then plugged in the value. Since there was nothing else to process there, plugging it in early is not a bad idea.
Would have been shorter to take the y prime out?
You got the same steps to do it. Only here you're multiplying binomials. Some of these are x cubed times x times y squared, and x squared y prime, and y cubed y prime, all like that. And boy, with the numbers.
It looks easier to take that y prime out when you just multiply everything. You know what I'm saying? Because you get that 3 times that 10 times that.
You got to multiply it before you take it out. It's in there. It's embedded in there. And you've got to deal with it first. You can't. There aren't really any shortcuts. Actually, plugging in the numbers made rather than carrying around x squareds and x cubes and y's and all those other things, we just had numbers. And I think numbers are easy to work with. So I like your choice. Yes? Oh, you don't leave us again, aren't you? Okay. Here we go. Let's see, where's your extra page there? All right. Which kind of reminds me, before we lose anybody, we're awfully close to midterm. And let's see, I've received 1 and only 1 paper from this class. And guess what? Only 2 from all 6 classes I've taught teaching. So please get your papers in. And you're getting the second test now. It means I really should have the first test in hand really soon. I should have already had it. But get those to me too. I hate for you to have 2 tests at once. Okay. Good deal. The other reason for that is I don't want you making the same mistake twice. Okay. So get them in so I can grade them. You can see, whoops, I wasn't doing that right. All right. So that's how we did it. I guess we get to watch how they did it. So let's see, and you tell me which way you like better, okay? They started off just like we did, only they wrote an extra step in here. They're going to implicitly differentiate this, which sure enough gave us 2 times 3, and they took time to write it that way, times x squared plus y squared to the first power, times the derivative of the inside, which is 2x, plus 2y, y prime. They like to write dy dx. That's a lot extra writing, but yeah, that's fine with me if they flips the vote. And here they did it this way. So what they did was pull the 100 out. No one in yet. Just pull the 100 out completely and take the derivative of that. Remember, that's the constant multiple rule. And that'd be x and y. Now the 100 is completely outside. You don't have to carry it on the inside. Okay? This 1 here is the derivative of x being 1. Okay? So x, y prime plus 1. Okay? Which is what you got with the 100 in there, but it's fine to leave it or whatever. Okay. Now, let's see if they do the same thing I did. Yes. They noticed that this was a 6 and there was a factor of 2. Pull that out and make it 12. Okay. Goodness gracious, what an unusual way to do this. Here's what they did. So this may be a hybrid between what they're doing. They looked here and saw this was a 12 times this times 2y. No, I'm sorry, they already pulled the 2 out. Okay. 6 times 2y would be 12y times this times dy dx. They did the second term, this stuff times this, did it here. To me, this is really confusing to do it this way. And then they took this term here and subtracted it over here, okay? Minus 100x dy dx. Then they took this term, well, the 100y here, and subtracted this one from it, which was the 12x, x squared plus y squared. Did that all in one step, which to me is pretty tricky of them, okay? Now they factored out, the next thing is to factor out the dy dx there, and you had, let's go back and see that, because we didn't do it this way. 12y x squared plus y squared minus 100x times dy dx. So that's what they got there, okay? And then on the other side, they just left it just like it was, okay? Now, next thing they're going to do, I think, is divide by this coefficient out here, which is exactly what they did. dy dx is now 100y minus 12x times x squared plus y squared divided by, and I don't know why they reversed this, but they put the minus 100x first and the plus there. Perfectly fine to do that, but mystery to me why they chose to do it. And now they're going to plug in the values. And frankly, all this carrying around stuff, I just as soon have numbers in there, all those x's and y's. It sure makes things easier. You get to cancel things earlier. You know. But anyway, when you plug that in, oh, no, now they're going to factor first. Okay. Yeah, we're going, what we had already done before, factor out a 4 from numerator and denominator, and that would be 25y minus this, 25y plus that. So, yeah. And then we'll get, now they plugged in the 3 and the 1, which is perfectly fine, and they get it down to 25 minus 90 over 75 plus 30, and that gave her minus 64 over minus 45. Oh, this is a joyous way of doing it, which is 13/9. I kind of like Nolan's way better, okay? here is what this looks like. This is obviously not a function per se. If you go back to the original shape, there it is up there. You see you got x squareds, y squareds, xy's in there. You got all sorts of combinations there you can't extricate, so it can't be written y as a function of x. Cannot at all, okay? Don't even try it, okay? So since it can't be written as a function of x, not at all surprising it comes up something that looks like this. By the way, the limit escape sort of comes from this side, and the tiltedness of it comes from the xy factor there. That's my crude way of looking at it. Okay?
What's the limit escape?
What's that?
What's the limit escape?
That. That's just what it is. It's a figure 8 shape. Okay? It's called the limit escape. And right now I can't think of really too many practical uses for it. Perhaps aerodynamics, maybe. I don't know, I'm just guessing. Pretty obvious things about it. There are 3 places where the first derivative cannot be defined. These 3 vertical tangents here. There are 3 places where you have horizontal tangents. There. And I can't think of much else of any interest. At the point 3,1, which is on that curve, the slope is 13/9. A little bit greater than 1. All right. That was example 5. My guess is they didn't do example 6. So let's go back and do example 6. I think this will probably be as good a place as any to do it. Find dy dx implicitly for the equation sine y is equal to x. Okay? Then find the largest interval of the form a or minus a less than y less than a, on which y is a differentiable function of x. Okay. Now, said first, find dy dx. How do you do that? Any ideas? dy dx.
You take the derivative.
Okay, how do you do that? Cosine y. So, say again.
Cosine y equals
Whoa. Okay.
0.
Okay. Now, I agree with the equal 1. Okay, don't change that. That part was okay.
Cosine y prime, y prime.
Okay, cosine y prime. That's it. See why?
Yeah.
Implicitly. Y isn't a function of x, so you have to chain rule, take it one more derivative. And now what does that give you? It said find dy dx implicitly. You're close, not quite there.
So we need to divide the 1 by cosine.
Yes. Divide both sides by cosine y, which includes the y1. Okay. And now you have y prime, or dy dx, is equal 1 over cosine y. Okay? Now, we have found dy dx implicitly for that equation. It says now find the largest interval of the form negative a less than y is less than a on which this is differentiable. Where would it not be differentiable?
Vertical tangents.
Say again?
Vertical tangents.
And where would that be? Anybody? What makes a vertical tangent?
Circle.
Second?
Circle.
The circle, is that what you said? Okay, circles certainly do have vertical tangents. Is there any hint this is going to be a circle?
No.
No. Okay. So a good answer, but it has nothing to do with the problem. Good. Okay. Where do you run into vertical tangents? What happens to make a vertical tangent? Oh, let me give you another definition for a vertical tangent. A vertical asymptote.
Okay.
Okay, does that give a hint? Where do those show up? Second? Vertical what?
Slope.
Yeah, vertical slope. Yeah, that's what we can't have.
Denominator equals 0.
Yes. Where you can't have a function defined, and that's where denominators are 0. What would make that denominator 0?
Cosine 90. No, yeah, 90.
Yeah, cosine 90, since you're thinking in, huh?
90 and 180. No, 90 and 270.
Okay. All right. You're thinking in terms of degrees, which is okay. Normally in calculus, we think in terms of radons or radians, or yes, okay. And what would they be equivalent? Second? Okay. Now you said 90. Second? Pi over 2 is 1.
And then 3 pi over 2.
3 pi over 2. Okay. Those would be two values for y for which you can't have that in the denominator. So if we stayed in between that, but what's wrong with that picture compared to what they're asking us?
It's supposed to be negative.
Okay, they're asking if what values of y, which you could find as negative a to a, these are both positive.
Yeah.
90 and 270 were both positive. So what would be a negative a and a you could have over which that defined?
Negative pi over 2.
Negative pi over 2 to pi over 2, I think you have it, okay? Negative pi over 2 to pi over 2.
Wait, it'd be pi over 2, not the 3 pi over 2?
Yes, I was getting my eraser to erase it. And these would be the values for y. Okay. Now, question. Did I mess something up here? Should that be less than or equal to? Should I have equal to in there?
Well, the one up there, that's logical.
Yeah, okay, I know. But what if that? No, the better reason is that 0, you can't do it, so don't put an equal sign in there. Okay, I'm going to go and erase the 90 since that's in degrees anyway. Okay. Whoa, I didn't erase it, did I? Okay. All right, I think we found what they were asking for which that is a differentiable function of x. Okay? Now, not quite there. They want it written as y as a differentiable function of x. Okay? And what we have is y prime, y prime and cosine y's. We don't even have an x in here. So we need to write this. Let me see if I can read the problem. Find that, blah, blah, we did. Then find the largest interval of the form of that, which we did, on which y is a differentiable function of x. Okay? So we need to change this to y as a differentiable function of x. Now, there's a couple ways you can go on this. What would be the way you would think of doing it? If you were integrating it, that'd be a great idea. I don't see that's all that helpful now. I think I know what you're thinking, but the word is just not quite right. Rather than anti, try inverse. inverse function. That was the first thing that came to my mind. Just write this as, get my...
Since cosine's a component of x.
What's that?
Isn't cosine a component of x?
Cosine of what?
Isn't cosine a component of x?
Okay, all right. You're on the unit circle now, and yeah, you're thinking in those terms. This is not necessarily a unit circle problem.
I'm just thinking of trig.
Okay, in trig, on the unit circle, cosine is x. Also, in trig, if you're not on the unit circle, cosine is x over r. It's just a unit circle, r is always 1, so it's just x. But we're not on any circle here, so we don't really have an r. So that is sort of a construct that we use for defining your trig functions. This is a completely different function. When we show the graph of it, which I was hoping not to draw, you'll see that it's not a unit circle or anything else like that. But yeah, it is kin to that, but not in this context.
I was just wondering in that term, since it's part of x,
well, you see, even that, you would introduce an angle theta. Cosine theta is equal to x. Even if that was working, well, there's no thetas anywhere in this problem, so probably not a great idea to do. But I think what I was hoping I was understanding you to say is take the inverse sine of this, and that would be y is equal to inverse sine of x. And that is certainly a function of x that's defined between those two values. That's not exactly what they were thinking of here. What they were thinking of here is, going back to trig again, if you, and this is a dangerous thing to do, but okay, why in the world are they doing that? Okay, I guess, okay. That's certainly true. This is. Here's something else that's true. Sine y is equal to, okay, without me doing too much of the talking here, start over. Tell me a relationship between sines and cosines that's always true. It's an identity, as in Pythagorean identity. Okay, in terms of sines and cosines, that's sine squared y plus cosine squared y, always equal to 1. Perfect. Now that's always true. Unit circle, not, it's always true, okay? Now, let's get that in terms of sine. Okay, I'm doing it differently from the way the book did it, because it says on which y is a differentiable function of x. So I'm solving for y, okay? Now, we know sine y here, so let's solve this for sine y. So what would you do first? Solve for sine y, because that's what you have over here.
So move that cosine.
And how do you do that? Subtract cosine squared y from both sides. Okay, perfect. And that gives you sine squared y is equal to 1 minus cosine squared y.
So then would you just square root it?
Yeah, you square root it, and that gives you sine y is equal to, square root of 1 minus cosine squared y. Okay, I did do it backwards. Okay. What I needed to do, it still gives me problems.
How come the cosine squared moved over
What's that?
When you're taking that square root, why don't that cosine go away? Or like cosine squared?
Okay. Because if that were a times here, it would. That would be the square root of the square. This is 1 minus a cosine squared, which you can't, you can't do a sum or a difference, simplify that under a radical, because they have to be multiplied or divided. Those just don't work. So that's not a rule. And you just can't do it, make up a rule. Okay, that's fine. Now, I was going to say this is equal to x, and then that gave me x is equal to the square root of that. So I sort of did it backwards. I should have subtracted the other way up here, okay, and subtracted the sign. That's what the book did, and I thought, why did they do that? Now I see why they did that. Ooh, I messed that up. Okay. Okay. All right. If you subtract the other way, whoa, wrong. Yuck. Okay. Subtract the other way. No, goodness gracious, this drives me nuts. Okay. Subtract sine squared y from both sides. Okay. It gives you cosine squared y is equal to 1 minus sine squared, which is, by the way, x squared, because sine y was x squared. Okay. And here's, say again? Taylor? Okay. I thought you said your name was Taylor. Kaylin! Got it. I'm sorry, my hearing is so terrible. Okay, I was thinking, this didn't sound right at all. Yeah, so I had already marked you here. I was psychic, and I already put you down as present. So, sorry. Glad you're here. That would have really driven me nuts. Okay. Okay. Now, what you do now is plug this, is take a square root of both sides, cosine y. Yuck. Okay. Cosine y is equal to the square root of 1 minus x squared. Now, I should be hearing screams of, wait a minute, isn't that plus or minus? And yeah, it is, except that we it goes back to the trig function. Cosine is like this, right? So from minus a to plus a, from minus pi halves to pi halves, this is always positive. So we don't have to do plus or minus, we just do the plus, okay? So now what we have is y prime is equal to 1 over the square root of 1 minus x squared, okay? Now again, to me, this isn't answering the question that they said. They said, find the large, okay, we found the interval on which y is a differential function of x. And we sort of did find it, but the thing is, they wrote it as derivative of y as a differential function of x, which is certainly true, but that wasn't, to me, exactly what they were asking for, but we'll let them get by with it. Sorry, that took way too long. Let me go on and do example 7. Wasted way too much time on that one. Sorry about that. Okay, example 7. By the way, this guy is featured in the book here, Isaac Barrow. Does anyone know who in the world Isaac Barrow was? He's not really that famous of a mathematician except for one issue. He was Newton's professor. He was the one who got Newton started, and Newton passed him in no time. He actually surrendered his chair to Newton. He had been the Lucasian chair of mathematics at Oxford or Cambridge, whichever it was, I can't remember. And he actually surrendered the chair and gave it to Newton because Newton was far superior, but he was the one who got him started. Now, he did other stuff, and we'll talk about this after this example. He discovered this general solution for the tangent line to this curve we're talking about, the kappa curve. Newton was Barrow's student, and they corresponded frequently regarding their work in early development of calculus. So he was the one that got Newton going. So, and he was one of the few people I think Newton didn't disagree with big time. I mean, they had a good relationship. Newton was an ornery old cuss, you know. So here is x squared plus y squared is equal to 25. That's what is given. Okay? It says find d2y dx squared. Okay, what are we going to have to do in order to find the second derivative of y? What you got to do first? What's the good answer? Find the first derivative. So let's do that first. What's that?
You just get like x plus y equals 5, right? You square root it.
You never give up on your rules for taking square roots,
I was
do you?
just saying, we ain't got to do it my way.
No. It's a plus or a minus. You can't take a square root and get rid of those. Only if they're multiplied can you do that, not added or subtracted.
I always think of it, I just don't worry about flipping.
Yeah, but quit thinking that way. I mean, it's wrong. You can't do that. With pluses or minuses, you can't take a square root and lose. And just ignore that. It just can't happen. You know, no way. All right. So how would you do that legally? How? Tell me the steps. 2x plus 2y y prime equal 0. Good deal. Now what?
Move that 2x over.
Okay, I'll take that means subtract it from both sides.
Yeah.
All right, and that gives you 2y y prime is equal to
2x.
negative 2x
And then you're going to divide
by 2y
get
y prime
equals x, negative x, over y.
Okay, good deal. All right. Now, we want to do the second derivative. So what do you suggest we do with that? Okay, do it.
Alright, so we're going to do the quotient.
Can I just do y double prime? No, I can't. Or yeah, I can? Okay.
Alright, so it's going to be negative x. Yeah, I'm doing the quotient.
Doing the quotient rule. How does that go?
So negative x
Okay.
times y prime.
Are you sure this is the quotient rule?
Yeah, because it's f of x times the g prime of x plus or minus g prime.
Okay. You don't like my little saying that helps you keep from messing signs up, do you? Low-D high.
Yeah.
Low-D high. Huh?
I can do that without low D high.
Yeah. Minus high D low. Okay. Over low low. Okay. That's helpful. Low, which is
Y. That's going to be nothing because it goes away. It'll be 1 minus 1.
minus. Okay. Good. I like it.
And then again,
You don't like your signs, do you? Okay. Next.
it's going to be a minus.
Minus.
Actually, it's going to be a plus.
Plus.
X.
X.
Y prime.
Okay. Wait a minute.
divided
by
y squared.
y squared. Okay. Now, believe it or not, you're almost there. But you've got y's in there. And
No, you can get rid of one of the y's. No.
okay.
Yeah.
Okay.
Would it just be x y prime over y? Since you cancel out that y on the bottom, or just cancel out that root or the square too.
Okay. You could if it was multiplied. Okay.
Yeah.
You can only divide things that are multiplied. Let's just make sure we have done it right. Yeah. Okay. Now, here's sort of the trick. Okay? Go back to this and solve for y, which is sort of a pain in the neck. Okay? But we're going to do it. Okay? It's going to be even better solving for y prime. I mean y squared. That's easier. And then you've got your y prime already here. So let's plug those in. So let's first do two things here. Take this and first solve for y squared. That's pretty easy. What is your y squared? I'm taking this.
Oh, there is going to be 25 minus x squared.
Minus x squared. Very good. Hang on to that. Then what is y?
It's going to be 5.
Say again?
Plus or minus.
Plus or minus. Very good. The square root of 25 minus x squared. Okay. Now, and you got your y prime. So if you do those, okay, now here's the problem, that minus y, which one do you minus? Does it really matter? Let's try to keep it simple and minus the minus one. It may give us something wrong. Let's try it. Square root of 25 minus x squared plus x times y prime, which is exactly this, minus x over y, right? There's your y prime right there, right? Okay. Over x, y squared, which is 25 minus x squared. Okay? Now, let's see if we can simplify this any way whatsoever. Square root of 25 minus x squared plus x squared over, oh, we still got a y in there, don't we? Plug that back in. The square root of 25 minus x squared. I should be keeping up with my signs better than I am. And this will be over only, I think I just messed up. That should be a minus because there was a minus there. Okay. I think I got it right now. Yeah. Over 25 minus x squared. Okay, in the numerator there, let's multiply and divide by, multiply numerator and denominator by this denominator. Okay? So that's going to give me 25 minus x squared. You multiply that by that, minus x squared, over 25 minus x squared times the square root of 25 minus x squared. Okay. Well, this really looks messy, doesn't it? This will be 25.
Wait, is there supposed to be a negative in front of that?
That's what I'm wondering.
Since if you're plugging in that negative
Yeah. No, okay. Yeah. Yeah, they do keep it a minus. Okay. So it'll be a minus 25 over, because, yeah, the minus here changes that to a plus. And then these go away, and you have minus 25 over. And this is 25 minus x squared to the 3/2 power, which, if you look at that, that's exactly y cubed. So this would be minus 25 over y cubed, which is not a function of x, but is a function of y. So why did we plug in the y's anyway? Sorry about that. I was thinking they wanted us to get it back in x's. We could have done it a lot easier if we kept it in y. Sorry about that. I thought they were trying to get it in terms of x's, but they weren't. So it's much easier to do it the way they did in the book. So, yeah. All right, sorry, that was convoluted. Sorry, didn't look ahead to see how they were going to give their answer. I thought they were going to do it in terms of x's. Let's do example 8, the last one. Finding a tangent line to a graph. Find the tangent line to the graph of x squared times x squared plus y squared equal y squared at the point 2 over root 2, which is really a bizarre way to write. No, I'm sorry, I read it wrong. Root 2 over 2. I was going to say, usually you don't write it that way. Root 2 over 2, root 2 over 2. I think I saw the two near to each other. Okay. Now, time out again. I like to make sure that point is on the curve before. Otherwise, you're going to waste your time. So what is, if x is root 2 over 2, what is x squared? Anybody? Second? I don't think so. Root 2 over 2 squared. It's what? Okay, square root 2 you get 2. You've got to square 2 also. 4, and what's that? 1/2. 1/2. Okay, so this is 1/2. These are 1/2 each. 1/2 times 1/2 is? Huh? 1/2 plus 1/2 is?
1/2 plus, would it be 1/2 plus 1/2?
Yeah, 1/2 plus 1/2. These are the same. So that's 1. 1 times 1/2 is 1/2. And this is 1/2. Yes. So this works. Okay? It is true. Now, it says find the tangent line to that graph at this point. So what are we going to need to know a tangent line? Need several things. To write an equation of a line, what do you need? A point. We got a point right there. We know that's on the curve. That's why we checked it out. So we got the point. What else we need?
Function.
Second?
A function.
There's our function. What do we need to draw to write the tangent line? A point alone won't give us a line. A slope. Very good. How do we get a slope? Take a derivative. Very good. So how are we going to do this one? Help me.
2x.
2x. That's a good way to start. Times.
2x.
Second?
2x.
Whoa. What are you? Huh? Product rule?
Living product rule?
I think so. He took the derivative of the first.
Okay. So then it'd be like,
Okay, you don't like to do it that way, do you? Okay.
You can't take the derivative of that, and it can't be 2xy.
Second?
I say you can't take the derivative.
Okay. The product rule says, okay, and there's two ways to do it. The first times derivative of the second plus the second times derivative of the first, or the way you were doing it is derivative of the first times the second plus the derivative of the second times the first. Either way will work. Some people are real stuck in their, no, never mind. Okay. How would you do it? If you take the derivative of this first, what do you multiply it by? The second, which is x squared plus y squared, right? Plus x squared times 2x plus 2y y prime. Okay, you've taken the derivative of the left-hand side. Next. Oh, okay, sorry. Didn't want to rush you.
Equals negative 2y prime.
Say again? 2y y prime. Very good. Okay. Now, what would you suggest that we do next?
Should we kind of, we could just multiply.
Okay, we certainly could.
Get rid of the c's.
Say again?
Or solve for y prime.
Okay, now I sort of like that idea. Okay, let's get all our y primes on one side and all the non-y primes on the other side. Now the trouble is it's easier to move this one that way because you already got the non-y prime here. I'm afraid we'll wind up with minus, but we can live with that. Okay. Or, and this may be what you were suggesting before, let's clear parentheses first. Were you saying that before? Let's do that. Okay, what would this be? 2x cubed plus 2xy squared, yeah. Help me. Plus 2x cubed plus 2x what? Squared y prime equal okay. Now anything pop out at you right now? Twos. Everything's got a 2 in it, so let's get rid of divide everything by 2. Everything on both sides. Say again? You could, but I find it easier to get rid of the 2's first. Now combine like terms. And what like terms do you see? 2x cubed plus xy squared. And let's go and subtract this from both sides, okay? Because that's got a y prime in it. Minus x squared y prime minus x squared y prime. Okay? So this will be on this side. That's gone. And over here you have a y minus x squared y times y prime, right? And now let's divide by y minus x squared y. Okay. Okay. Now, I think we found our y prime now. What we got to do is plug in that value. So what will that give us? Let me clean it up a little bit. Y prime is equal to 2x cubed plus xy squared over y minus x squared y. Now let's plug in those values down here. And what do you get? Anything? let me make maybe a suggestion to you that may help a little bit. I was going to make it earlier, but y'all already figured it out. I'm going to tell you another way to write this one. Isn't that the same as 1 over root 2, 1 over root 2? Isn't the square root of 2 over 2, 1 over root 2? Yay or nay?
You say yeah, why yeah?
Because I'm a cheerleader. No, okay. How do you get, why did we get that? We multiply numerator and denominator by root 2, right? That gives you root 2 over root 2 times root 2 is 2. I was thinking back in trig. That's the 45 or the pi fourths, root 2 over 2, that was 1 over root 2. It's just, that's what it is, okay? And to me, I find, see, if we had done that here when we were plugging in, that would be 1/2 times 1/2 plus 1. It would have been much easier to do than when you did it, you forgot to square your denominator. You do it this way as 1/2 obviously, right? So, plugging that in here, it's going to be messy in one place, maybe more than one, but I think we can live with it. Let's see what we get. Okay, 2 times 1 over square root of 2 cubed. Maybe not, but let's see. Minus 1 over root 2 times, well, what's 1 over root 2 squared? Help me. Second? 1 over root 2 squared. Y squared. Second? 1 over 2. Yeah, that's 1/2. Okay? Over 1 over root 2, that's your y, minus, and x squared is 1/2 times 1 over root 2. Okay. Now, I want you to notice something here. This winds up with a root 2 in the denominator because you cube it, right? That has a root 2 in the denominator. This has a root 2 in the denominator. That has a root 2 in the denominator. What's that again? Oh, that's a plus there. Is that the one you're talking about? Yeah, you're right. No, you're right. That is a plus. It always was a plus. Nothing but a plus. So what I'm going to do is multiply numerator and denominator by root 2. Okay? And what that's going to do is take out one of these and leave me a 2 down here. It'll take out that one altogether. Okay? It'll take out that one altogether and that one altogether. Okay? Now I've lost all my root 2's. So what we have here is, if I can read it, 2 times 1 over 2, that's just 1. That's 1 plus 1/2 over 1 minus 1/2. Okay? You know what I'm going to do? I'm going to multiply everything by 2. Okay? And this will be 2 plus 1 over 2 minus 1, which is 3. Goodness, can it be that simple? Yes, it was. The slope is 3. Yeah. All that just to get that. Now, I was really surprised when Nolan didn't want to plug in this right in this step right here. It would have made it much easier, but it would have made it a little bit, I think. Because you did that before and it worked out nicely. But we came up with 3, and that is the slope. So what do we do with the slope? We have the slope, we have a point. What is the equation of the tangent line? How do you get that? Equation of the tangent line. Second? And how does that go?
Y minus y sub 1.
Okay, which is your 1 over root 2, or root 2 over 2, I don't know which one to use here, is equal to your slope, which is 3 times x minus 1 over root 2. So that is y minus 1 over root 2 is equal to 3x minus 3. It's probably going to be better putting root 2's over 2. 3 root 2 over 2. Make this root 2 over 2. Okay. Sorry, I'm changing in the middle of the stream here. Okay. And then what we're going to do is subtract root 2 over 2 from both sides. No, add root 2 over 2 to both sides. Yeah. Okay, and what does that give us? I'm going to erase some stuff here because it's just in the way. Okay, erase too much, I think. Okay. Y is equal to 3x and I believe that comes out 2 root 2 over 2 because this is minus 3 root 2 over 2 plus root 2 over 2. That's minus 2 root 2 over 2, which is minus root 2. I think. Yes, that's exactly what they get. Sorry that was all over the place, but a small board, it's hard to do that many calculations. But there's your equation of the tangent line. Y-intercept is negative root 2, slope of 3. And I still have not quite figured out which one of these is the kappa curve. Is that the one we just did on example 6? I mean, they talk about the kappa curve in Isaac-Barra, but they don't say which one of these is the kappa curve that I've figured out yet.
I think example 8 is right next to
it. Was number 8?
Yeah.
Okay, it may be. Oh, there it is. Yep, it's listed there. In the figure, it says the kappa curve. Okay. All right, finally, we finished 2.5. Homework exercises here. Any of the odds, 5 through 19. All those odds are at calcchat.com. Number 5 is at CalcView. 21 or 23 are both. They're both at CalcChat. 23 is at CalcView. Any of the odds 25 to 31, they're all at CalcChat. 25 is at CalcView. Either 33 or 35, they're both at CalcChat. 33 is at CalcView. By the way, on that one, it says these are some famous curves, and that first one is called the 33 is called the Witch of Agnesi, okay, which is a terrible translation. What happened is it was a word that I believe in Italian or Latin or something, someone miscalculated it. It was supposed to be something else, and they mistranslated it as a witch, and it's not anything to do with a witch, okay? The sad part of it is Agnesi was a woman, so they tied this word witch in with her, and that's terrible. She was one of the very earliest famous, incredibly talented women in mathematics. They just didn't happen back then. She was the Agnesi who's here, and it's a shame they have it Witch of Agnesi, okay? So that may lead to a paper topic. And then there's the folium of Descartes, and I think we've mentioned Descartes before. You could use him as a paper topic as well. Or how did she develop that curve, or how did he develop this folium, whatever. Other famous curves, either 37 or 39, they're both at CalcChat. 39's at CalcView. Oh, I'm sorry, 37 through 41. They're all at CalcChat. 39's at CalcView. There is an exploring concepts at 43. You can fiddle with that if you want to. I don't know if the answers in the back of the book or at CalcChat, either one. But number 45 you can certainly do. It's a CalcChat. 47's both the CalcChat and CalcView. Any of the odds 49 to 53, all at CalcChat. 53's at CalcView. 55's at CalcChat only, as are either 57 or 59. I'll let you choose which of those are both at CalcChat. 61's at CalcChat. 63's at either 63 or 65. They're both at CalcChat. Neither are at CalcView. And then 67 and 69 deal with orthogonal deals. So they do some new definitions here. Orthogonal trajectories, that kind of stuff, they define here. Also tangent lines and normal lines. We'll do these tangent lines we've done, but normal lines we haven't. They define them here. We'll do those later as well. 71 is another equation of a tangent line. They're getting a little more difficult here, but 73 is a proof. You can do it or not, and 75 is another tangent line. And number 77 is a normal line. So you can do any of those that you would choose. Okay. And I was going to say we'll just do a quick slideshow of related rates. We really don't have time, I don't think. Let me just tell you this. Let me read a problem to you. Well, when water is drained out of a conical tank, the volume V, the radius R, and the height H of the water levels are all functions of time. Knowing these, you can differentiate implicitly with respect to T to obtain a related rate equation. Because when you're taking the derivative, especially with respect to time, you come up with a rate. You get the rate change of the volume, rate change of the height, rate change of, what was the other thing? The radius. All those, you can do a rate of how they're changing as you're draining your tank. So the point here, when you have a problem, example 2, pebble is dropped into a calm pond causing ripples forming concentric circles. You've probably done that. The radius of the outer ring is increasing at a constant rate of 1 foot per second. As soon as you see that, the radius, so dr dt is equal to 1. It's right there. A rate is a derivative with respect to time, just about always. And that is the key to doing this, to solving the equations. Once you have the equation set up, we've already been solving them. You just go through and solve them. So that's what's involved with related rates. A rate is a derivative with respect to time. I wish we had time to do that. They're sort of fun, but we really don't. Now here's the other thing. I should have warned you early on. By the way, we finished chapter 2 except for 2 point, whatever that was, 6 or 5? 2.6, okay. There are some review exercises starting on page 161. These are odds are at CalcChat. They don't have any of these at CalcView. So you could do either 1 or 3 if you wanted. You could do 5. You could do 7. You could do any of the odds 9 through 19. Any of the odds 21 to either 21 or 23. 25, 27. Any of the odds 29 to 39. Any of the odds either 41 or 43. Any of the odds 45 to 51. You could do 53. Any of the odds 55 to 65. 67 to 71. 73 or 75 or both. 77. Any of the odds 79 to 81. And then 85. After that, they get into related rates, so you don't have to do those. So I'm saying you don't have to do those, but these are just, if you need some more to review, there they are. So, any of you here who did not get a test for this chapter?
Chapter 2.
Chapter 2.
I didn't get chapter 2.
You need chapter 2 test?
Yeah.
Okay. Let me find it. I just had it. That's test 1. There we go. Oh my goodness gracious. It's sitting too long. What's that? Oh, sure.
If that pens and equals,
You didn't get one last time?
numbers there, you hand them out.
Oh, I had somebody early on.
Yeah, one person.
Okay, I thought I had handed these up. Well, I guess that's right. I remember y'all were leaving the right answer. I said, oh, I wanted to give you the test, but everybody was already gone. I had meant to talk. Okay. All right. And by the way, pretty much down the way, 1 and 2 are from section 2.1, 3 and 4 are from 2.2, 5 and 6 are from 2.3, 7 and 8 are from 2.4, and 9 and 10 are from 2.5. Okay, so it's just 2 from each section. We didn't do related rates. All right, now the other issue here, and I should have told you this early on, this morning when I went to get my car, I almost dropped my watch because the pin broke. So I don't have a watch on today because it fell apart. And, huh?
We got 10:04. 10:04.
10:04. Okay. So I'm going to get out of this. Are any questions on chapter 2 before we leave chapter 2? Okay. So let's discard this and get out of this and go to 3.1. Now that sounds and feels like a good time to take a quick break. Y'all mind? Because I need a bladder break, sorry. I thought this was opening, I guess it still is. So I'm going to put this on pause back. Chapter 3 is applications of differentiation. Okay? Now, if you look at the first part of the chapter, page 165, 9 sections. That's a lot. That's a lot to cover. So what we're going to try to do is go through these, and there's not many of them that we can skip too much. Yes?
I'm just asking, are we going to be, is this the chapter where we talk about intervals or something?
Okay, that's chapter 4.
Okay.
Okay, chapter 4 is, this is such a long chapter, integration. So that's the last chapter we'll do. So
is this approximations?
say again?
Is this are we doing approximations?
We do a little bit of that. I'm trying to think if it's here or later.
You know what I'm talking about? You do the L, and then you do the M, and then you do the R. You heard of that? It's like you do the L.
Okay.
It's like you take a curve, and then you like...
Okay, that's a linear approximation, the L.
Yeah.
And what were the other two you
And
said?
then you do the midpoint, and then you do the right point. It's like,
Okay. Oh, okay. No, you're not talking about linear approximation. Okay, you're talking about Riemann sums from the left, the right, and the mid. Right. Yeah, we're going to do some of that. I'm going to try to minimize that.
It's like the one with the sigma, and then there's like an
Exactly.
I star equals something.
Right. That's just like we began the derivatives with limits. We began integration with rectangles, and that's where you do left, right, or midpoint.
Mm-hmm.
Okay, and then you take the limit as the interval gets smaller as your number of intervals increase goes to infinity, and that's how you get integration. So your sigma becomes an integration. So yeah, we're going to do that. That's chapter 4, though.
Yes.
That's chapter 4. And we'll get into that. I wanted to get into 5. I don't know if we're going to have time. We're going to have to really hoof it to get into 5. And the reason I wanted to get to 5 is that's where you hit exponential functions, logarithmic functions, and those kinds of things, which you really do need when you get into Cal 2, okay? But we are rapidly running, we're right awfully close to midterm now. We're going to miss, unfortunately, next Wednesday. So, and these are 2 really long chapters, chapters 3 and 4. So how much of 5 we're going to get to, I don't know. It may be a really rush job right at the end. So let's get hopping on it. 3.1, extrema on an interval, okay? And we'll try to do these as quickly as possible. I hope they're not going to be going so fast you can't understand them. So, first thing, understand the definition of an extrema on the function of a function on an interval. Now, that may be a new word to you, extrema. Anyone familiar with that word? It's the plural, because it's, I think, from Greek, of extreme. Extreme, or extremum, and then extrema, okay? It's a plural.
These are from interval notation.
Second?
These are from interval notation.
Okay.
Interval notation. The opening interval and closing interval is, but I do know extreme for something else, like when you stretch the graph or something like that.
Okay. Yeah, and what we're talking about here are maxima and minima.
Yes.
Yeah, okay. So that's what we mean by extrema. Understand the definition of relative extrema of a function on an open interval. And I tell you, they beat these things to death, okay? There is sort of a reason for it, but I think you can live without going into as much detail as they do, and I'm probably spending too much time to say that. And we'll find extrema on first an open interval, then a closed interval, okay? And they really do beat this to death. So let's try to move through it quickly. In calculus, much effort is devoted to determining the behavior of a function on some interval I. Okay? Now, here are the questions you ask yourself. Does that function have some maximum value on I? Does it have a minimum value on I? Where is the function increasing? Where is the function decreasing? Okay? And those questions are all sort of related to each other. In this chapter, you'll learn how derivatives can be used to answer these questions. You'll also see why the questions are important in some real-life applications. Okay? So here's the definitions of extrema. Okay? Let F be defined on some interval containing some point C. So F is some function defined in some interval that contains this point C. That means F is defined everywhere there. There's no places where it's not defined. Now, F of C, C is on that interval, so F of C is the defined quantity. That is a minimum of F on C when F of C is less than or equal to every other F of X on that interval. Okay? So if this is your interval and here's your F, whatever the lowest or the least value the F has on that interval, that would be your C value if that's your minimum. It's the maximum if that's the greatest F value on that. The F of C is greater than or equal to all the other F of X's on that, for all X's in that interval I. Okay? The minimum and maximum of a function on an interval are called the extreme values or extrema. See, extreme values is plural, extrema is plural. Singular form of extrema is extremum. Okay? In the Navy, when we were at sea, and the worst situation you could have if you had a contact out here, also on the water, and you had what they call constant bearing decreasing range. That means even though they're very far apart and going different directions, if the bearing didn't change and the range decreasing, that meant at some point you were going to crash. And that was when the rules of the road came into play. And the rules of the road, one ship was required not to change course, and the other one was required to change course until you reach what they call extremum. And that is, if you don't do something, you're going to crash. Then the one that was required to maintain his course would do whatever it took to keep him from colliding. Because otherwise, if you both start changing, you don't know what the other one's doing, and you wind up colliding anyway. So, but that's where I use the term extremum. You reach the extreme situation. And those are called the extrema of the function on that interval. The minimum and maximum of a function on an interval are also called the absolute maximum, minimum, and the absolute maximum. Okay? Or another term, global minimum, global maximum on the interval. The extrema can occur at interior points or at the endpoints of the interval. Okay, and we'll show that in just a minute. Extrema can occur, if they occur at the endpoints, are called endpoint extrema. Okay, blah, blah, blah. Okay, a function need not have a minimum or maximum on an interval. Okay, and we'll talk about this. Show the picture. For instance, in this figure, here we have a f is continuous on this interval, -1 to 2, continuous there. It has a value at the endpoint, it has a minimum down here, it has a value at the other endpoint. That happens also to be the max, okay? So the maximum's here, the minimum's here, that's E, okay? Now, if you don't count the endpoints, okay, f is continuous on the open interval. By the way, they call this the closed interval. That's why you have solid circles at the end. If it was an open interval, parentheses here, not brackets, then that means you don't count the endpoints. Okay? Same function, same everything, f of x equals x squared plus 1, continuous on the interval. However, here, you're not including the endpoints. Okay? Well, sure enough, this is still the minimum value. So it does have a minimum, but this one has no maximum. And that seems a bit bizarre when you say it's the point just before you get to 5, right? But there is no point just before you get to 5. You can get infinitely close to 2 here, and you still keep getting closer and closer to 5. So you can't find a value 1.9, 1.999, 1.999999999, but not 2. You can always get closer to it, but you can't ever reach a max. So this does not have a maximum because that endpoint is not defined. Okay? It's open value there. So this would have a minimum, but no maximum. You know where the maximum would be if you defined it, but it doesn't have one. All right. Here's another. Continuity or lack thereof can affect the existence of an extremum on an interval. This function is not continuous. Remember, the earlier said it was. The f was. This one's not. It's continuous down to here, but then at g equals 0, g at 0 is defined to be 2, not 1. So as soon as you take that out of the picture, now you don't have a minimum, and this one does have a maximum. If you had this on open interval, then it would have neither minimum or maximum. Okay. So here's the theorem you get from that. When f is continuous on a closed interval, a to b, closed interval a to b, f has both a minimum and a maximum on that interval. Guaranteed. If either of those are open intervals, you may not have one of those. If it's not continuous, you may not have it at all. Okay. But if it's a closed interval, A to B, you're guaranteed to have a minimum or a maximum on the interval. There may be some interior point for either one, or it could be an endpoint for either one. But it's got to have a maximum or a minimum. The only, to me, problem function there would be a horizontal function. Then every point on the line is both a minimum and a maximum because they're all the same. Okay? And that's sort of a nebulous case. Okay? So, that was pretty much page 166. Now let's look at relative extrema and critical numbers. Now, if you wondered why they called that C in that interval, here's why. Okay, this is called the critical number. So they didn't tell you that beforehand, but it is. In this figure, the graph of f of x equals x cubed minus 3x squared, there's a picture of this graph, has a relative maximum at the point 0, 0. Now, why do we call it relative maximum? Because this isn't a closed interval. This goes on forever. And since it goes on forever, it's going way past this value. So it doesn't have an absolute maximum. This is not a closed interval, okay? But it does have a relative maximum. That means for any values of x close to 0, then your y never exceeds that value 0 anywhere close to that. Over here is not close to it, okay? Over here at what, 3 or 4, somewhere there, yeah, it's exceeding that. Who cares? Relatively speaking, that's and what they call it here, that's the biggest hill in the area, okay? So that's your relative maximum. That's what we call it relative maximum. It also has a relative minimum down here, not an absolute minimum, because this keeps going south here without end. I mean, it goes on forever. But in this general area, that's your nearest value. That's as low as you can go within some reasonably close value to that point. Okay? So, relative maximum at 0, 0, relative minimum at 2, 4. 2 for x, negative 4 for y. 2, negative 4. Okay? Informally, for a continuous function, you can think of a relative maximum as occurring on the hill of the graph and the relative minimum occurring at the valley on the graph. Anywhere close to it, you don't exceed the hill, you don't get any less than you do in the valley. Okay? So those are your relative minimum and maximum. Okay? Such a hill or valley can occur in two ways. When the hill or valley is smooth and rounded, the graph has a horizontal tangent line at the high point or the low point. But when the hill or the valley is sharp or peaked, then the graph represents a function that is not differentiable at that high point or low point. Okay? Now, examples of that. Oh, well, we're going to give the definition first. Okay. I wanted to see the example first. This is a smooth curve, relative maximum. This is a pointed curve, relative minimum, but this is not. We'll talk about the differences here, okay? That is a relative minimum here, but it's different from being smooth. Here we have smooth, so relative maximum and relative. Okay? We'll come back to that in a minute. Here's your definition. If there is an open interval containing C, on which f of C is a maximum, then f of C is called a relative maximum. In other words, if there's some open interval that is a maximum, you can make that as small an interval as you want, that is a maximum, then f, and it's an open interval, so you can't have the endpoints. You have to have an interior point. It's called a relative maximum of f, and you can say f has a relative maximum at C, f of C. Why C? We're going to call that a critical point later. If there is an open interval containing C, such that f of C is a minimum, then f of C is called a relative minimum at f of f, or you can say it has a relative minimum at C, f of C. The plural of maximum is maxima. I heard a trivia question once. Most car, I don't know what you call it, names, like a Buick Century or a Plymouth, they don't make them anymore, the Dodge Caravan, the Dodge Charger, Toyota Camry, most of those names like that are singular, except for one. Think of what it is. Now, you could argue Chevrolet Impala that could be singular or plural, like here is singular or plural. The one that is strictly plural, and it's rather bizarre, the Nissan Maxima. It's a plural name. One of the few ones you'll ever see that's a plural. I don't know what that is. I think that's a made-up word. Okay. Ultimatum, that would be an ultimata, but what is an ultima? I don't know. A lot of the, and I blame it on the foreign cars, they sort of start making up ones. So I don't know. Maybe it is. It may be. I don't know. All right, but back when they first came out, that's the first one I knew of. So anyway, the plural of this and the plural relative minimum is relative minima. The relative maximum and relative minimum are sometimes called the local maximum or local minima as well. Okay. And together called local extrema. Okay. So here's example 1. Find the value of the derivative at each relative extremum shown here. Okay. Here's the function, and it tells you that's the relative maximum. So we need to find the derivative of that. How would we do that? Anybody? There's 2 ways you can proceed with this. At least 2 ways. Which way would you go to find the derivative of the function there at that point? How do you take this derivative? Tell me.
Quotient rule.
Okay, I knew he was going to say quotient rule. Okay, so let's do it. How does that go? F prime of x is equal to
18x.
Okay. I hear him saying 18x.
Yeah.
Minus.
No, what is that? Is that a 9? I can't see.
It is
Okay.
9.
This is 9x squared minus 3 over x cubed.
I thought I saw parentheses at the end of that 3.
It is.
9 minus 3 in parentheses. 9 times x minus 3, x squared minus 3 over x cubed.
The a squared minus 3.
X squared minus 3 is in parentheses.
Oh, then that 9's not going to be 18. If the
Okay.
x squared's in the...
I didn't know where you got the 18. I thought that's where you got it.
I didn't see the parentheses. I was just doing the power rule.
Okay, wait. Let me. All right. Let me. Yeah, okay. All right. Start me off again with this. Well, yeah.
You have to do this.
What's that?
Did you just distribute the 9 across to that x squared minus 3?
Or you want to distribute first?
I was just wondering, could you?
You can, absolutely. You want to do that first?
Yes, sir.
So we'll rewrite this as what?
9x squared over, or 9x squared minus 27.
Okay. And just do it that way. Okay, that's perfectly fine.
Alright, now you can take the derivative. It's going to be, let me do it on paper.
I can't hear. Sorry.
I'm going to do this on paper.
Okay. Someone else want to tell me what to write?
Isn't this 18x?
Second?
18x.
You're starting with 18x2, is that right?
18x is the power rule.
What's that?
18x.
By the power, I understand that.
Alright, so I'm doing f of x times g prime of x minus g of x times f prime of x.
Okay.
F prime of x.
Whereas f is what, the numerator or the denominator?
F is the numerator.
Okay. So you're doing a new quotient rule.
And then d low, or I'm doing d high low minus.
Is that how it goes?
Well, that's the way I'm doing it.
Okay. Okay, that's fine. Okay. So d high was 18x.
Yeah. Times. Because the 27 goes away. Okay.
Okay.
And it's going to be times, and it's going to be 3x squared.
times x second.
3x squared.
Wait.
Down there, right?
Yeah,
Huh?
it's
Yeah, but, okay. I thought you were doing the d high times low.
Yeah, the low is going to be, it's going to be
Oh, yeah, huh?
x cubed.
Ah, okay, so that's x cubed, okay, got it. Minus
And then your original function, 9x squared minus
9x squared. What?
positive. No. Would it be a positive 27? Because that minus.
Okay, I got what you're doing. You're removing parentheses at the same time. Minus 9x squared plus 27.
That's right?
It depends on what thought comes next.
Well, then it's just going to be times 3x cubed.
Okay, now I don't know how to write that.
And then you got to do it over.
Okay, yeah, but see, the way I've written it now, it's just this times that, not that. So I really wanted to put that in parentheses, which means don't change the signs yet.
Okay.
Because that has to be times high, right?
I was just wondering if that 27 becomes positive.
No, if I do it the way that I think I have to, I think it's a safer thing to do like that, because that's now your high d low, okay, minus high d low, which I think is what you were saying, right? Now, all what?
And it's divided by x cubed squared. So
Which
that'd be
is?
x5.
6.
6.
Yeah. When you raise a power to a power, multiply the powers. If you're multiplying x cubed times x
Cubed. It'd be,
squared, you add the exponent. When you're raising it, you multiply exponent.
Okay.
Yeah. Okay.
That makes sense.
Okay. So, and what we want to do ultimately, we want to find the derivative at that point. Okay. So you want to plug in now, or do you want to simplify this first and then plug in?
Can we kind of get rid of some of the parentheses?
Let's try those. Okay. And what would that be?
18x
18x to the fourth.
minus 27. What? 27 x to the fourth.
Right.
Minus plus. That's gonna be 81 x squared.
Okay.
And then we can get rid of the 18 and the 27 and just get minus 9 x squared.
Okay. What's this again?
Well, the 18 and the 27 have common.
Oh, yeah, right. Okay, right. Got it. Okay. So that would be minus 9x to the fourth plus 81x over x to the x squared. Okay. That right?
And then can you get rid of the x's?
Some of them.
Okay.
Which ones?
Get rid of, it'd just be negative 9 plus, it would be negative 9 squared, x squared, plus 81 over x to the 4.
Perfect. Okay. Now, that's about as simple as we can get it. That's 81. It's a really ugly 81, but that is 81. Okay. Now, what we want to do is plug in x equal 3. And what do we get the slope to be?
Negative 81 plus 81 over
We can stop there, can't we?
81.
No, it's more than that. It's 247, 240.
Wait, isn't x 3? So
Oh, I'm sorry. You're right. X cubed. Okay, sorry. X to the fourth is 81. You're right. Okay. I'm sorry. I was doing 9, not 8. Not 3. Okay, sorry. Over 81. Okay. And what does that equal?
0.
0, okay. That numerator is 0, the whole thing's 0. Okay, no matter what, as long as the denominator is not 0, and it wasn't. So, sure enough, at that relative maximum, which they told us that was the relative maximum, sure enough, the first derivative is 0. Okay? And hopefully this comes as no surprise to you. Because what are you doing as you're approaching that? Your derivative is very steep here, very large positive number, but as you get closer and closer to that, it's getting less and less positive until you reach that maximum, and then it's 0 and then starts going downhill. So positive, 0, and negative. And this positive is getting less and less until you reach 0, and then greater and greater. Negative. So yeah, that's it. What about your first derivative of this function? It's the absolute value function. What's the slope of the line coming in here? Second, I can't hear. -1. Okay. So what's going out here? 1. Okay. So what is it? 0.
Would it be 0?
Undefined.
Undefined.
The limit as you come in is not the same as the limit coming the other direction.
Yeah.
So it's undefined. So it does not exist. Okay. How about the sine function? Okay. First thing we got to do is find. They've given us a relative maximum. What we need to find is the derivative there. What's f prime of sine?
Cosine.
Cosine x. What is cosine x at pi halves?
0.
Yes, 0 again. How about the minimum? What's cosine at 3 halves? Pi. 0 again. So sure enough, it looks like, and it is indeed true, that you have a relative maximum where your horizontal, your slope is your tangent line is horizontal, where its slope is 0, 0, 0, or undefined. Only 2 options you can have. And therefore, we'll name these as being our critical values. X equals 3 is your critical value, x equals 0, x equals pi half, or 3 halves pi are your critical values of those functions.
We have 2 minutes.
Second?
We have 2 minutes. Almost 1 minute now. We have 2 minutes. Almost
2 minutes.
1 minute.
All right. Oh, shucks. We ran out of time, didn't we? So derivative of this there, they finally got around to doing theirs. They did low d high minus high d low over low low and got that as a simplified form. And when you plugged in the point 3, x equal 3, no matter what the y was equal to, you got f prime of 3 was equal to 0. So the slope, the slope of the tangent line is 0 at that relative maximum. This one, the derivative did not exist because it was a one-sided limit, -1 from the left, +1 from the right. No limit exists, so it doesn't have a slope at the x equals 0. Okay? And they did those limits here. And derivative of that is cosine. And at those 2 points, pi halves, cosine is 0, and at 3 halves pi, cosine is 0. So the slopes are 0 at both of those critical values. Though in example 1, that at each relative extrema, the derivative is either 0 or does not exist. The x values of these special points are called your critical numbers. Okay, or I like to call them critical values, but they call them critical numbers. The 2 types where the first derivative doesn't exist, here it's going to positive infinity this way, going to negative infinity that way, it doesn't exist there, and here the slope is 0 there. So both of those are critical points. So here's your definition of a critical number. Well, that might not be a bad place to start next time. So this will be the top of page 168. I'm guessing, whoa, this is a very short section. Yeah, and you can do any of the odds, 7 through 11. They're all at Calc Chat, 7's at Calc View. And we'll hold off and do the rest of those next time. Okay, good deal. Any questions? All right, then we'll say have a good couple of days. We'll see you on Wednesday. All right, got a test coming in. Thank you.
Does it bring out papers to you, or do we turn in on Blackboard?
I don't have it set up for you to do on Blackboard. If you mean email me through Blackboard and send
I
it.
thought maybe you put me up.
No, I just, yeah. Because I like to see your work. And usually if people send me something on Blackboard, all I get are answers. Now, he only gave me answers, so I just have to grade it. But, yeah, I like to see your work. That way I can get partial
Okay,
credit.
I was talking about the research paper.
Oh! Yeah, you can either send that to me by email or bring it in person. The research, the advantage of printing it out is you look at it and see if it is indeed the format you want. It's not often, but I have had them in the past that when I print them out, I think, do they know what this looks like? Because if it's all screwed up, and if you're just looking at the screen, you may not see that. But you know, it's up to you. I'll take them either way.
Okay, also, Miss Dressy stopped me this week.
What's that?
Miss Dressy, she stopped me this week and said she was trying to contact you. Have you spoken to her?
Okay, Mr. Rusty, what?
She stopped me last week and said she was trying to contact you for a while. She wanted me to tell you that she's trying to contact you.
Okay. Say that one more time.
She's trying to contact you.
Oh, Mr. Rusty?
Yes.
Yeah, I've been in touch.
Okay.
Oh, I'm sorry. I thought you meant it was something new. Okay. Thank you.
Two things. One was going to be about, do you have time today, like your office hours?
Yeah, between 2 and 6, basically.
To make sure you can be there. Like, you didn't have anything planned, like the doctor's visit or anything.
Well, usually I eat lunch sometime between 2 and 3, but you know, other than that, I'm in there. I brought my lunch. I eat in my office, so I can do everything.
Also, with the papers, if we bring them to you in person, can we get like critiques before we turn them in, or do we just turn them in?
Okay, what was the first part of that?
If we bring in a paper in person, can we bring them in for critiques as opposed to just turning them in?
Since I got so many to grade, I only want to grade it once. So do your best shot and send me that grade it. Okay. You can ask me if it's a good topic or something like that. That's fine. If that's what you mean by critique, but
just look at it and say, hey, this is acceptable, or hey, this isn't acceptable based on formatting and like how you want it exactly.
the format and that kind of stuff is completely up to you, but you just need to be consistent with it. Yeah.
Okay.
Uh-huh.
I'm good.
All right, you too.
Can you work with something similar to number 10?
What's that?
Can you work something similar to number 10? Like on the
What
test?
about number 10?
Can you work something similar to it?
Okay.
I'm kind of confused on that.
Yeah, can you find one in the text? that's
Yeah,
similar?
sure.
Okay. I'll work anything in the text. Unless it's exactly the same problem, I'll hesitate doing that. Okay. So let me see. Goodness gracious. All right. Let me get out of this. Okay, we are in chapter 8. Eight 3. All right. While you're looking for that, because I don't mind doing it in class, so
Yeah,
everybody
you
can
can
see
do it
it.
in class,
Let me
don't
run down and just get clear my head a little bit, and also I'm going around by my office and pick up a little something to drink. My throat is getting fairly raw feeling. So I'll be back in just a bit. Oh, I need to mark this too. I'll get back here as soon as I'll turn off the director. So on the bug a little bit.
just got back.
Oh, okay.
I didn't really have my phone or laptop for like a week.
Okay.
It was nice.
Okay, this is the first test, right? Okay. Wait. That's L1, sorry.
Oh, yeah, I'm down to take that one.
Okay. You better do well on that one. Okay. I think that's it. No? Maybe. I think that's it. Yeah. Anyone else need the first test? Okay. Everybody got it? Okay. Let me mark the roll, and then we'll get to your question. Connor is here. Corbin is not here yet. Can't read my writing. I think it's Ariel, not here yet. Justin Brown is not here yet. William is not here yet. Brendan, not here yet. Justice is here. Elijah's not here yet. Terrell is not here yet. Jeremy's not here yet. Clark's, I don't know. I think he's going to withdraw. Hasn't yet. Nacoma's not here yet. Bailey, right? All right. Anhil is here. Preston is here. 3 in a row. All right. Okay. Davis is here. 4 in a row. Patrick, though, is not here yet. And Brandon's not here yet. 1, 2, 3, 4, 5, 6. 3 and 3, 6. Got it. Okay. Now. All right. We're starting today. Oh, let me turn on the projector. And let me warn you ahead of time and ask a favor at the same time. This morning when I went to get it in my car, my watch fell off my arm. The pin snapped or broke or something like that. So I don't have a watch today. So you'll have to let me know when it's time. Because once I get off of this, I can't see the clock on my computer either. So let's get this set up from the current slide and get Screencast-O-Matic started again. Oh no,